Hi students, welcome to video 20. It is on nuclear half-lives. So when we're talking about nuclear half-lives, we're talking about nuclear energy. And the whole idea here is that the elements are radioactive, or at least some of them. So not all elements are, but certain ones are radioactive. They emit radiation. They emit different particles from their nuclei. So as these elements are decaying over time, they're going to change from one element to another. So for example, we might have uranium-238, and uranium is going to eventually decay into lead. Now, they all take different times, so that takes a very long time, 2.5 billion years, about the age of the Earth. And then we also have something that's a little bit more useful for humans, carbon-14 dating, which is a lot faster, so it only takes about 6,000 years. So here's a couple of terms you need to know, or facts that you need to know. A half-life is the time that it takes for literally half of a substance to decay into the new material. And then you can take another half-life and you would end up with 25% of the substance. You can keep on going. Every element has its own unique half-life, just like we saw before. So we can use those elements to actually do something in terms of dating the time of different materials. The half-life of a substance always stays constant. We just have to assume that because it's what we've seen in the past and it's what we expect to continue to see. So it's kind of like a clock that keeps time for us. So how is this useful? Mainly for us for fossils. So trying to find out how old certain things are. We can do this with fossils. We can do this with rocks. We can look and see, okay, well, we know that it was 100% carbon-14 at this time, and now we only have 10% left. So we can use the half-life to determine how old that substance might have actually been. You also can use it in something like forensic science. So ricin is one of the materials that you may have seen if you like forensic files. They talk about it all the time, where this has such a short half-life that if someone is poisoned using ricin, you will not see any evidence of this after about a week. It will be completely gone. Maybe I shouldn't tell you that, but oh well. So ricin is something that's so quick, it goes away very fast, and so it's used in forensic science as a detection of a poison if you can get it fast enough. So let's look at an example of how we would actually calculate percentages and things like that. So the blue in this case is going to be our parent material, meaning is what we started with, and the red is going to be our daughter material, what we are ending with. So the blue in this case is carbon-14. It is decaying into nitrogen-14. So we start out with 0 half-life. So at time 0, when that animal has first died, it is all carbon-14. So 100% of the carbon-14 that was in that animal is still there. After 1 half-life, it has decayed into 50% nitrogen-14. So now we're not carbon anymore. We have decayed into nitrogen. So we're at 50-50%. By the way, I would at least, if I were you, I would write at least the first 3 columns here. The ratio is not so important, but it's good to have these percentages in your notes. After another half-life, so after 2 half-lives, only 25% of my carbon-14, my parent material, is there, and I have 75% of my daughter material. And after 3 half-lives, I have 12.5 and 87.5. And I can keep on going. I could go to 6.25 and then 3 point whatever, all the way until I'm almost at 0% for my daughter or my parent. So you do notice that my parent is going down, it's decreasing, going all the way to 0. It can actually go to 0. And then my daughter is increasing, it's going all the way to close to 100%. So I do have right here, this is the half-life. So 1 half-life would be 50-50. Here's another half-life. If I go to the next time this elapsed, and I'm at about 75-25, and you see exactly what we just calculated from there. But with this information, I can actually use a graph to represent and figure out what the half-life of a substance is. So if I had 100% of a parent, I'm looking for where do I have 50% of the parent. So that is my half-life. I went from 100 to 50. So if I go over and I can simply hit the graph, and then I can go down and I can look. Well, in this case, it's a nice whole number. It is 1 million years is the way that that is written. So the half-life for this substance would be 1 million years. So here's a problem for you. A sample of iodine-131 had an original mass of 16 grams. How much will remain in 24 days if the half-life is 8 days? So take a second, pause the video, and actually try this one on your own. Okay, so now hopefully you've tried it. Let's see if you got the right answer. So the first step you should have done is to get how many half-lives did we actually go through. So you take the total time elapsed and you're dividing it by the half-life. So we had 24 days and we're dividing it by 8 days because that's how long the half-life is. So we went through 3 half-lives in this situation. The next step is you start with how much mass you had. So we had 16 grams to start with. We take 1 half-life. So at 1 half-life, I'll have 8 grams left. Okay, but I don't have 1 half-life. I said I had 3 up here. So my second half-life, now I take half of that. So now I have 4. And then finally, I hit the third half-life, and I have to take half of 4. So I would have 2 grams. Okay, if my answer was 4 half-lives up here, I would keep going, and I would have 1 gram. But in this case, the answer to our question is how much is going to be left. That will be 2 grams. Okay, let me know when you have questions. We're going to practice some of this more in class as we keep going.